So, welcome back friends to the course on quantum mechanics and the relativistic frameworks. Okay, so we have been looking at our first relativistic wave equation or wave equation for relativistic quantum mechanical wave equation for relativistic particle or the counterpart of Schrodinger equations in the relativistic case given by the so called Schrodinger the Klein-Gordon equation. The Klein-Gordon equation is given by this, which has a Lagrangian also for later sense. For later reasons we have introduced the Lagrangian, and then this has solutions, as we have seen. It has solutions both which are positive and negative essentially. So, which are positive and negative, okay. And then okay, one second. Okay, which are both positive and negative. So, the point was because they have negative positive energy solutions as well as negative energy solutions. So, initially we started with the idea that we will have a single particle wave equation, but the moment we make it into a relativistic wave equation, what happens is that they become you end up having both positive and negative energy solutions. So, essentially it becomes a multi-particle equation. Okay. Now, the second thing is how do you interpret this negative energy solutions essentially. That was also what we have discussed, and we have discussed that it also leads to negative probability densities essentially if you look at the continuity equation of the Klein-Gordon equation. So, we have seen that it leads to negative probability densities because of the time derivatives in the definition of the probability densities. So, this is what we have looked at. So, if we have two time derivatives in the equations of motion, the continuity equation would have a first derivative in the in time in it, and this leads to problems with negative charge density, negative densities, negative probability densities. So, then we realize that it is not in the best way to introduce interpret them in terms of probability densities, but instead we interpret them in terms of electric charge densities. So, if you have electric charge densities, you have one particle with positive energy, a positive electric charge, another particle which has negative energy with negative energy charge, and these both, now you can interpret this positive this equation in terms of charge densities and current densities. In that sense they can be negative. So, if you interpret them in terms of positive energy densities and negative charge densities, negative charge densities, they can become negative. So, there is no contradiction with our interpretation. So, this now how do we couple interpret it as positive and negative energy densities, charge densities. So, for that we have to couple it with electromagnetic field. I have shown you how we can couple it with electromagnetic field. Essentially you have to introduce a relativistic electromagnetic field strength tensor, and with that you introduce the A field, which is also the vector potential field, which is nothing but the photon field, which is nothing but the photon particle essentially, or and then you write a Klein-Gordon Lagrangian with respect to which is coupled to the electromagnetic field, and then you can write the corresponding charge and current densities, and then you can interpret it in terms of so in terms of electric charge and electric current densities essentially, and then there is no real contradiction. Now, this is how you couple in your Klein-Gordon field equation essentially or in the Klein-Gordon Lagrangian. This is how you couple the electromagnetic field to the Klein-Gordon Lagrangian essentially. In other words, you can write you can derive the Klein-Gordon Lagrangian also with this essentially, which we have shown how to do it essentially. Now, at the end of the day we said that the Klein-Gordon field, now what now the point is that we claim that this is all fine because this is a relativistic particle, but it has two particle interpretation, one with positive energy and one with negative energy. The positive energy has positive charge, electric charge, and negative energy has negative electric charge, but still how do you know what happens in the limit in which we actually go to a non-relativistic limit. Say for example, if we do not, do we get back our Schrodinger equation or not essentially? No. So, because Schrodinger equation is a one particle solution essentially, okay. Are we going to get back this thing, because in the relativistic sense we have two particles, one with negative energy, one with positive energy. So, this is a problem essentially. So, how do we get back do we get back Schrodinger equation in the non-relativistic limit? Now, this is the question we have to ask essentially. Now, the Klein-Gordon equation in the non-relativistic limit is what happens to it? Now, for that it is simple to realize. So, to begin with we just have to see understand that the Klein-Gordon equation started with the dispersion relation E square is equal to P square plus M square, which is the relativistic energy momentum mass energy momentum relation essentially. Now, in the non-relativistic limit what happens is this relation E is equal to root of. So, in the limit non-relativistic limit this will become P square. Now, expanding when the mass is much higher. So, the non-relativistic limit is in the limit P is much smaller than M. So, this gives me you can expand it around M essentially. This gives me P square by 2M plus a series essentially. This gives me a series around M essentially. So, this you realize is nothing but your kinetic energy term in non-relativistic quantum mechanics, or in classical mechanics also it is the kinetic energy. And now, when you quantize it or make the quantization conditions on P and E, this will give you your Schrodinger equation. In fact, this is what. So, what you expect from taking the non-relativistic limit of the Schrodinger of the Klein-Gordon equation, you should get back your Schrodinger equation without any modifications. So, because if you see from the dispersion equation point of view, you should get back the thing essentially. This is what we should expect essentially. So, let us recall the Klein-Gordon equation, and we will see how to get back what is the Klein-Gordon what is the system, how do you get back your Schrodinger equation from Klein-Gordon equation. So, the Klein-Gordon equation, as you recall very well, now what I want to do is we have to choose let us take free particle, we are not putting any interactions like no electromagnetic interaction or anything essentially. Now, I made statements in the previous lectures that the Klein-Gordon equation always represents spinless particles, meaning particles with 0 spin. Now how do we see it? I did not give you an argument that it should always give you meaning it should always why it should represent spinless particles. I did not give you any argument essentially. Now the argument can be seen from taking the non-relativistic limit. If you get back the complete Schrodinger equation without any spin term essentially, that means this represents a spinless particle essentially. That is a basic idea, that you have already shown that in the non-relativistic limit you do not have any spin like sigma matrices or anything, and that is one way of showing that the Klein-Gordon field Klein-Gordon wave function always represents spinless particles. There are other ways actually, so a little bit more mathematical, depending upon using the properties of the Lorentz group itself. If you use the properties of the Lorentz group itself, you can say whether the particle is under the Lorentz group, if the particle transforms like a scalar, such wave functions or such wave functions the wave functions being represented representing the particle represent scalar particles, essentially spin 0 particles. That is one more way of looking at it. We will come back to it at in a different lecture, but for the present let us do the non-relativistic limit essentially. So let us define a non-relativistic wave function. Okay. So essentially we take a wave function, or essentially this would mean that we are choosing a frame where the mass of the particle is plays a very low momentum. So we are choosing phi nr is equal to n0 e power I mt, it is a non-relativistic wave equation, times some phi tilde x of t. Okay. So now what is the momentum is playing a very small role essentially. So you see that what I have put input the wave function itself, it is a massive wave function. Okay. That means the mass part is playing a very big role, the momentum is very small essentially. Okay. It is not on the same footing. So we are already considering a free you are putting in a wave function which is non-relativistic essentially. You are putting in a solution which is non-relativistic, and what happens this is that now going back to the thing, you have del square t square minus del cap square plus m square phi nr is equal to. So you take this wave function, which let us just take a non-relativistic wave function, put it back with some arbitrary normalization essentially. Okay. You take a wave function, but it has e power minus I mt, that means the momentum part is the p times x is very small, so that is the assumption. So you have only, instead of E you only have mass, you put it back into the Klein-Gordon equation. Now traditionally what you would say that if this will this satisfy the relativistic wave equation, and you know that it will not satisfy the relativistic wave equation. Okay. Will not satisfy it. Now the point you have to do is that now if you take the energy of this wave function essentially, this is given by the time evolution of this wave function del by del t of this wave function, which is essentially this phi tilde, our test wave function, is much smaller than mass itself. The mass of the particle essentially is m, because you are going in the limit in which it is highly ultra non-relativistic essentially. Okay. In that case if you assume, make this assumption that you are in the limit in which the kinetic energy of the particle is very very small than compared to its the mass essentially, then what you can do is del square phi of nr by del t square is equal to del by del t. You can expand this. Okay. So, you can take this term, the first term of this equation, which is this, okay, and expand it in this particular fashion. You are just putting back into this, there is nothing new in this, you are just put it back del square by phi m n t, and you expanded the just substituting back in this. Now you say now okay, now you expand the derivative, take the derivative, you get now okay, I will use the black pen. Now you end up having this relation where because I just took the expansion derivative with respect to the exponential essentially. So, what I did from the previous step is nothing but I just expanded the derivative, okay. I expanded the derivative, took the derivative, okay. This gives me this relation essentially. Now you see this 2, you have minus phi del n r minus m square phi del n r, okay. Now this gives me maybe I have to just be careful with my notation. I think I should put it as phi tilde essentially, I have been putting it as phi tilde. So, this gives me minus psi 2 mi to m So, you end up with a relation I think yeah okay L square phi n r, okay. So, now you keep it back. So, what is happening here is that the derivative, the time, because the time derivative with respect to this, one of the time derivatives with respect to this is essentially equivalent to the massive part essentially, and putting it back everything into this equation, let us call this equation as 1, okay. So, you end up having, so you can the first derivative essentially the double derivative of time is converted into a single derivative essentially, and then you end up having the equation as nothing but your Schrodinger equation in terms of phi tilde essentially. So, you have H cross is equal to 1 del by del t phi tilde. This notation is not correct. Okay. So, put this back in 1. So, the basic idea is that this is del square essentially. So, you start with here an equation which is double time derivative essentially with a del square plus m square plus phi n square essentially. Now, what you want to do is start with a solution of phi which is in this particular fashion in such a way that if you take the non-relativistic limit essentially you start with a very limit in which p is very smaller than m. Okay. P is much smaller than m. You can expand this. Okay. And then now the same thing you want to argue in the presence of a wave function essentially that if you have, so what happens to p less than very much less than m essentially you can expand it around in this particular fashion. Now, if you take in terms of the time derivatives you have the del square terms essentially phi of nr and then there is the two terms which is del by del t and m square phi nr. Now, if you take the del square term which is much smaller than m, okay, now you can take the double derivative. Okay, if I take the double derivative of this essentially it gives me phi of nr del by del t and taking the exponential term essentially it gives me this particular fashion. Putting it back, okay, the double derivative will look like this particularly essentially, okay, and the m square term gets cancelled and you end up having 1 by 2 m square essentially del phi square by del square essentially. Okay, 1 by 2 m del phi by del t here the m square term gets cancelled and for the wave function which is non-relativistic you end up having the Schrodinger equation. So, this is another way. Now, the derivation is straightforward and simple. The only assumption you are making essentially is that the first derivative is much smaller than m and the rest of it is straightforwardly follows essentially. Now, Schrodinger equation it does not have any in the derived Schrodinger equation just by taking the limit where the mass of the particle is much the mass term of the particle contributes much more to its energy compared to the momentum term. What you end up having is the Schrodinger equation for a free particle without any spin terms essentially without any spin terms. So, this proves this again shows that Klein-Gordon equation represents spinless particles. Now the field is complex, the wave function is complex. So that means you have positive negative energy solutions. There are two solutions, positive energy and positively charged. They need not be the same essentially, but anyway, okay, let us just put it that way. Negative energy, say negatively charged, they need not be correlated, but it depends upon the sign. Okay. Negatively charged. Okay. Now note that this is I am putting a star, this could be, you can modify this essentially, negative energy negatively charged. So, but what happens if you have spinless neutral particle? What happens if you have a spinless neutral particle? Then phi is equal to phi star. Say for example, if you have a pi 0, say for example, which is also one of the particles essentially in nature, then you need to represent it with a real Klein-Gordon equation. With phi is equal to phi. So, real wave function with phi is equal to phi star. So, this is only for spinless neutral particles, meaning particles which do not have any spin like pi 0, the Higgs boson or many other particles which we encounter in nature. In those cases you introduce this particular case essentially, that you introduce the case when you introduce represent those particles with real wave functions of the Klein-Gordon equation, because there is no antiparticle for these particles essentially. So, the antiparticle is itself, they do not have any other antiparticle, whereas for charged particles, because they have antiparticles, they have to be represented by complex wave functions. So, charged particles, so remember that charged particles are always represented by complex wave functions, whereas neutral real particles are always represented by real wave functions. Okay. I will stop here and we will continue our discussion on Klein-Gordon equation before further proceeding to Dirac equation. Okay, I will stop here.